Welcome back. We're almost there. This is the last part of the stoichiometry where we're going to be determining the empirical formulas. We're starting at question 26. There's question 26, 27, 28 to go. So let's see if we can get through this lot, shall we? Right, first of all, what do they mean by determine the empirical formula of the following? And they give us something that looks like this, 26. Question A, they tell us, and they say Al of 53.2% and oxygen of 46.8%. Essentially, we are combining aluminium and oxygen, aren't we? We're combining these two. There's only two atoms in here. There's an aluminium and an oxygen. So we're combining them. But we don't know how many aluminiums and we don't know how many oxygens, do we? So in essence, we know that if we combine them, it's AlXOY. Correct? We don't know how many aluminiums are there or how many oxygens. All we know is we know that they've given us a percentage that it contains. Right, so where do we start? All right, what do? We say, right, let's make up a table. The element, let's put aluminium and oxygen down. Then let's put percentage, this is all given, 53.2% and oxygen 46.8%. Right? We're trying to find X and Y, aren't we? That's what we're after here, okay? Because we don't know how many aluminium atoms are bonded to how many oxygen atoms. Okie dokes. Let's carry on. Now we say righty-ho. Then we say, right, how many grams is this? All right? How many grams? Well, 53 here's the trick. You make them grams. 53.2 grams and 46.8 grams. This must be equal to 100%. That is then 100 grams. Okay, can you see what we've done there? There is the little trick. We've moved them to grams, right? The next thing we're going to work out, mm, right? And what is mm of aluminium? It's 27 grams per mole. And oxygen is 16 grams per mole. And the next step is to work out, yep, you got it, number of moles as per usual. We say, how many moles is this? Well, how do we get it? N is equal to mass over molecular mass, molar mass, right. I know I'm using those interchangeably at this point. Okay, let's just not bother about that too much. All right, let's have a look now. Therefore, number of moles is going to be, we've actually got 53.2 grams divided by 27, which gives us 1.97. Okay, gives us 1.97. And over here, number of moles is going to be mass 46.8 divided by 16, which comes out to be 2.93. All right. Therefore, what does this mean? This means it's actually going to be Al 1.97, O 2.93. But hold on, we can't have 2.93 of atoms of oxygen. So we round them up. It is Al2O3. Okay, these are very, very straightforward jobs. Not a problem to do at all. Now they're saying, they're giving us another one. Okay, let's have a look. 56, this is number B. Now in B, we've got a few more to play with. 56.5%. I'm just going to go straight to the table to save time. So let's put in our element. Okay, is K. And the percentage is 56.5. Then we've got oxygen, and that is 34.8. And lastly, we've got carbon, which is 8.7%. These are all percents, right? Therefore, let's change them to mass. 56.5 grams, 34.8 grams, 8.7 grams. That's 100 grams, and that's 100%, correct? Then we say, right, what's the mm of these guys? Right, let's have a look. Okay. The mm over here is going to be, where am I? Let's have a look. Oh, there we go. 39, 16, and 12. Okay, therefore we calculate number of moles. Mass over molecular mass, which is going to be what? We're going to get, over here, we're going to say the mass, 56.5 over 39. And we're going to get 1.45. This one is going to be 34.8 over 16, which gives us 2.175. And over here, we get 8.7 over 12, which gives us 0.725. Okay, so that's number of moles. Well, now we have to do some fancy footwork. We can't put, this is our, essentially, this is going to be K, okay, this is actually K subscript X, O subscript Y, C subscript Z, isn't it? And now, can you see we've worked out X, Y, and Z? X, Y, and Z, right? But they are not whole numbers, and we cannot have bits of an atom, all right? We are not breaking them up into quarks and things like that. We are just keeping them as whole atoms, all right? What do? We divide through by the smallest. I'm going to put that in red. You divide through by 0.725, which gives 1. Divide by 0.725, divide by 0.725. We want to get all these equal to a whole number, and we get 3 and 2. Okay? Therefore, our formula is going to be, okay, K2CO3. All right? Okay, question C, moving along. All right? Question C. Question C, let me just go back over here. All right, well, I can read it from the answers that I've got here. First of all, we've got C and O. So let's put in element. Copper. No, Kevin, that looks like calcium. That's Cu and O. Okay, and we've got 88.8. This is the percentage. 88.8 and 11.2. And yes, they must add up to 100%. Change them to a mass. That's 88.8 grams. 11.2 grams over 100 grams. Let's work out. That is 63.5. This is 16. Okay, therefore work out number of moles, mass over mm, right? Which is going to be 1.4 and 0.7. We rearrange, divide by the smallest one to get a 1, and divide by 0.7 and we get 2. Therefore, we get Cu2O, which means this was copper 1, correct? That was copper 1, wasn't it? How did I know? Because you always take the valency of the most electronegative, okay, which is oxygen, is -2. Therefore, copper is +1 to get a +2 because there's 2 of them. 2 copper atoms joined into an oxygen atom. Okay. The next one is question D. Okay, let's just slide up a page. Question D is chlorine and fluorine. Now, this is a weird one, isn't it? Question D is chlorine. Okay, let's just put in the table. Element 38.7, 61.3. Oops, Kevin wrote down the percentages, didn't he? Okay. 38.7 is chlorine and fluorine. So we say 38.7, 61.3. Okay, change it to a percentage, to a mass. 38.7 grams, 61.3 grams. Check you got 100, check you got 100%. Like that, right? Then the next step is to find the molar mass is going to be 35.5, and it's always grams per mole, and fluorine 19 grams per mole, right? Divide. In, we get 1.09, and over here, a 3.2. Okay? Now what do? We manipulate it, correct? We divide by the lowest. Divide by 1.09. Divide by 1.09 gives us a 1 and a 2,94. So basically, it's Cl ClF3. It is chlorine trifluoride. Okay? Now, why I'm doing these is I'm doing it it doesn't matter what they give you. It doesn't always have to be stuff you know. Don't panic. If you see things you don't know, just apply the same recipe. Look at this one, E. Okay? I mean, that one was weird. Come on. I mean, chlorine and fluorine reacting, come on. I mean, seriously? They do under certain circumstances, right? Remember what we said. We can make a lot of things happen that you'd be surprised would, okay? Given the right circumstances, okay? No, the inert gases don't react. Hello, you get compounds with xenon in it, right? So we manipulate things so it happens. Let's have a look at E. P, the element is phosphorus and bromine, right? So let's have a look. Percentage 7.19. Over here, 92.81. Make them a mass. 7.19 grams, 92.81 grams. Okay? Now let's have a look. Aha. MM, 31 and 80. Right? So therefore, N, the number of moles, is 0.232. And here is 1.15. Divide by the smallest one to get 1. Divide by 0.232, and it becomes 4.94. Therefore, what have we got? We've got P is 1 and BR 5. And no, we don't generally write a 1, do we? Okay? All right. All right. Let's have a look at the next one, which is F. Okay. F, they've given us the element NO. Okay. And it is percentage 30.4, 69.6. Okay. Mass 30.4 and 69.6 grams. Okay, MM is 14 grams per mole, remember? And oxygen, 16 grams per mole. N, number of moles, is 2.17 and 4.35. Divide by 2.17. Okay, divide by 2.17. And we get over here 1 and 2. So therefore it's going to be NO2. Okay? And, okay, then we're now moving on to question 27. All right? Question 27. Okay? Those are quite straightforward, aren't they? Okay, to work out those. Find the molecular formula. Now, this is a different kettle of fish altogether, isn't it? Okay? Find the molecular formula. The compound in question E above has a molar mass. So the question, this is question 27. The compound in E above, okay, has a molar mass of 431 grams per mole. Okay. What is the molecular formula? Whoa. Right. Let's go back to the question, okay? And we're going to say question 27a. It's the PBr one, right? So we had, right? Remember we had PBr, all right? And we worked our way through and we got it was PBr5, right? PBr5, right? And what we're going to do here is we're going to now work out the molecular formula of this. Okay, so let's have a look. Right, PBr5, right? So P is going to be equal to 31 times 5 plus bromine is 80, correct? Okay, let's work it out. Okay, 31 times 5 is equal to 155. And this one is going to be 80. Okay? And I can see there's an error in this, but I'll change it when we get there. All right? PBr is that. So what I've got here is I know that my molar mass is going to be a total of 155 plus 80 is equal to 235 grams per mole, right? 235 grams per mole. Now they told us in the question, okay, that we had that it was 431, okay? And, okay. So I just want to change that 431, okay, to 235 times 431 is going to be, oops, a daisy, that's a bit much. It's 235 times 2. Take that to 470. I want to just change it over here. 470 grams, okay? I interchanged digits when I did this thing, okay? So what do we say, right? We say the molar mass that we worked out is 235, but the actual molar mass, mm, is going to be, and we wrote it down, it's 470 grams per mole. What does it mean? It means that this is not PBr5. Why? Because PBr5 weighs 235 grams. This other stuff that's composed of PBRs weighs 470 grams, which means it must be 2 and 10. Okay? We're going to double it up. Okay? It's a 2 and a 10. Okay? Right. Let's look at the next one. Question, whoops, I need another sheet of paper there. Let's look at B. Right? B, they said, let's go back. B, they said the compound in F above, right, which is the NO2, has a molar mass of 92. What is the molecular formula? So B, the given, okay, mm is equal to 92 grams per mole. And what did we work out in F above? Right, F above was NO2. This is what we worked out, right? We calculated that, okay? Now they tell us, what is the molar mass of this? Well, it's going to be 14 plus 2 times 16 is going to be 46 grams per mole. Whoops, not 64. 46 grams per mole. This is the actual one, and this is the calculated one. Can you see the ratio is 92 over 46. So 2 is the ratio. So the actual compound is N2O4, isn't it? Right? It's N2O4. Right? Let's have a look at the next question. Question number C. A compound with the following composition has a molar mass of 60.1, and then they give us the compositions. Can you see this is just a variation on what we've done? This is the way they like to ask them. We say, okay, compound of the following has a molar mass of this. Can you see what they've done? They've said element. Okay, element is carbon, once again, hydrogen, and carbon, okay, hydrogen and nitrogen. Okay, carbon, hydrogen, and nitrogen. Okay, what have we got? We say the percentages again was 39.97. Let me just read it off my back sheet. 39.97. Okay, 13.41. And over here is going to be 46.62. That is 100%. Now we change this to a mass, right? Which is going to be 39.97 grams, 13.41 grams, 46.62 grams. Total of 100 grams. Seen this somewhere before? MM 12, 1 and 14. Okay. Grams per mole, grams per mole, grams per mole. Correct? Therefore, number of moles is going to be 3.33. Okay. 13.4 and 3.33. Therefore, we divide each one by 3.33. And what do we get when we do that? We get 1, 4, 1. So therefore, we are C1H4N. Okay? C1H4N. Okay? Right, then what do we do next? The actual molar mass. Okay? Therefore, the actual molar mass, all right, over here is going to be the actual mass is 14 plus 4 plus N, which is going to be 14. Okay, and I always write carbon 14 for some obscure reason. 12, all right? So we say, right, this is going to be 30 grams per mole, right? And what is the next one that we've got? The next one is the actual, okay? Oops, sorry, that's the theoretical mass, my bad. This is the theoretical, is that one. The actual mass that they told us is going to be 60 grams per mole. Therefore, it's got to be C2H8N2. The ratio is 60 over 30, which is 2. So we multiply everything by a 2. Okay? Quite straightforward, is it not? All right. Right, let's do question 28 now. All right. Question 28. Okay. I'm going to go over a few minutes now, but let's finish it off. Sodium carbonate reacts with dilute sulfuric acid. Write a balanced chemical reaction. And then they say, assuming this, assuming that. Let's have a look. So, first of all, let us write our, balanced chemical reaction. Sodium carbonate, sodium Na. Carbonate, CO3. We need to balance it. This is a +1, this is a -2, so we need 2 of those, right? Okay, and that goes to be H2SO4. What have we got? Acid and a carbonate. What are we going to get? Okay, we are going to get a salt, sodium, and sulfate, plus CO2 plus H2O, correct? That's what we're going to get out of this. Now let's balance it, and we have a look and we see it's balanced with ones, okay? It's balanced already. The next then is we write down the ratio, don't we? The recipe. Let's do it. 1 plus 1 cup of that is 1 cup of that, 1 of that, and 1 of that. Okay, now we put down what we are given. And they tell us 12 grams of that, okay? And they say 12 grams of sodium carbonate, okay? Calculate the concentration of sulfuric acid if it was in a 200 ml flask. Okay, so we've also given over here volume equals 200 mils. Right. Can you see where we're going? We're going to be doing the same again that we've always done. Okay, and let's have a look. Okay, so we say, right, is going to be, work it out, is 106 grams per mole, and this one is 98 grams per mole, okay? Now, this one is 142 per mole, this is 44 grams per mole, and this is 18 grams per mole, correct? Right, now we work out, okay, we're going to work out, right, 12 grams are reacted with that, okay. Let's work out, how do we work out? We know there and there, so we work out number of moles. We know a mass and we know a molar mass, so we can work out number of moles, and if I do that, it's 12 over 106. Let me just check my arithmetic. Is going to be equal to 0.1132, correct. 0.1132 moles. Okay, and what have we got? This is the mole whole again, isn't it? This also, by the way, works very well for acids and bases to do it this way. Okay, instead of trying to remember formula or manipulate, works pretty well for it too. So we say, okay, 0.11. Now, straight away, we can say, right, 0.1132, right, because that's 1, 0.1132, 0.1132, and 0.1132. Okay, like so. Right, then the next one is we say, okie dokes. What do we do here? All right, we've got everything we basically need. Therefore, they've said concentration, which is N over V. What didn't I do? Okay, I didn't do my usual trick. That is equal to 0.2 decimeters cubed. Okay, always remember, I remember it because I'm trying to jog it to you to always go back and make sure that you put everything in your units at the word go. So therefore the concentration is 0.1132 over 0.2, which is going to be equal to, if my arithmetic is 0.566. Okay, moles per cubic decimeter. Okay, then the next question is, they say, the amount of any gas given off in grams and the volume at STP. Okay, now they were leading us to say that we need to have a look at the CO2 over here, right? So first of all, how do we work out what the mass of CO2 is, right? Okay, right. We've got over there, all right, we've got the table, so we can work out what the mass is going to be, can't we? Because we know the mass of CO2 is going to be equal to number of moles times mm. And the number of moles is 0.1132. I didn't finish that off. 0.1132. Okay, times, and its CO2 is, I think, 44. 0.1132 times 44 is going to be 4.98 grams. All right, and at STP, hang on, STP trigger STP gas, 1 mole is equal to 22.4 decimeters, cubed, right? How many moles have we got? We've got 0.1132 x. This is what we're looking for, the volume, right? What do? Cross multiply 0.1132 times 22.4 equals x times 1. Therefore, x is the volume of gas, correct? Is going to be 2.54 decimeters cubed, or if you like, 2.54 liters over there. Right, we have done 10 sessions of about 30 minutes each, okay? As we build up the site, we'll do more. People are going to say, please do sections on this and more on that, etc. I hope that going through this and you doing it together, I hope we've made a big dent in your chemistry knowledge, and I hope that it's given you a good feeling about chemistry, because it's a wonderful subject. It's really, it's something to get excited about. We need more people involved in chemistry across the world, okay? We're facing huge changes coming, and chemistry is going to be a big part of that. Thank you so much for watching. I do appreciate it. I really hope that I've helped in a small way to make it better and give you more confidence. If you're unsure or whatever, you can always watch again. And when you're coming up to the exams, please, if you want to email extra questions or suggestions or whatever, please feel free to do so. But good luck, and from the bottom of my heart, I hope to see you in next year's. But I hope you have a good result, and I hope the chemistry is no longer a problem subject to some people. I hope there's a bit of passion for it now. Thanks for watching again. Cheery bye, and good luck with the exams. Bye.